Hey everybody, welcome back to Chem 305. Today we're going to be talking about chemical equilibrium, which is section 9.7 in your textbook. So far in this class, we've talked about one-way reactions, where reactants are converted into products. And we always show this with this one-sided arrow to clearly show that all of the reactants are made into products. And so we could say in this case that the products are favored, that the way the reaction is going to proceed, it's going to convert everything into products. And if we think of the reaction as kind of like a balance, all of the reactants get used up. So this side gets basically lighter, and this side, all the reactants are converted into products, get heavier. So we say products are favored in this type of reaction. But in reality, many chemical reactions are what we call reversible. And in a reversible reaction, the conversion of reactants to products, or the forward reaction, and the conversion of products to reactants, the reverse reaction, can happen at the same time. So we denote reversible reactions in chemistry by using this double-headed arrow to show that reactants can be converted into products, and simultaneously, products can be converting back into reactants. And so to show non-reversible reactions where it's a one-way reaction, all of the reactants are only converted into products, we use that single-headed arrow. And to denote a reversible reaction in which reactants are converted into products and products can be converted back into reactants, we use that double-headed arrow. And so depending on the conditions in these reversible reactions, our scale can essentially be tilted one way or the other to favor making products or to favor making reactants. Or we could keep the scale perfectly balanced with an equal conversion back and forth between reactants and products so that neither side is favored over the other. So it's like, right, if we favor producing products, most of the reactants are converting to products. This side of the scale will get heavier. We say we favor products. Or if the reverse reaction is favored, we favor products reverting back to reactants. This side of the scale gets heavier and we say that reactants are favored. And if both directions occur at the same rate, so that neither side is gaining products or reactants, then we say the chemical reaction is in equilibrium or it's balanced. And so you wouldn't get a scale tilting one way or the other. Every time reactants converted to products, at the same time, some products are converted back to reactants. And so this is kind of the definition of chemical equilibrium. It's the state in which forward and reverse chemical reactions occur simultaneously at the same rate, or they reach what's called steady state. And so when a reaction has reached what we call equilibrium, the concentrations of the reactants and the products no longer change. If we're thinking about the scales, when a reaction reaches equilibrium, reactants are being converted into products at the same rate as products are being converted back into reactants. So there's no net gain of reactants or products on the scale. It's staying perfectly balanced. And so again, we use that double-headed arrow to indicate that a reaction is reversible. And when a reversible reaction is occurring in both directions at the same rate and reaches eventually this steady state, which means that the concentrations of reactants and products are no longer changing, we then say that the reaction is in equilibrium. So I'm going to give a couple examples of equilibrium reactions in the real world to hopefully make this have a higher impact and make more sense. The first is on altitude sickness, which is an imbalance between the oxygen concentration and oxygenated hemoglobin in the blood. And then the second example will be on the production of fertilizers for agricultural use with the Haber-Bosch process. So example one of equilibrium. Altitude sickness. It affects about 50% of people who live at low elevation and then sleep at 10,000 feet or above. And some of you may have felt this, like if you live down in the valley and then you go up way up high in Tahoe to the mountains or elsewhere, If you start to get a headache, you feel woozy, you feel dizzy, some people get really confused. And that can be very, very dangerous when climbing, because if you feel woozy and dizzy, your decision-making skills can change, and climbers start to make poor decisions at high elevation if they're suffering from altitude sickness. Then they make mistakes and they get hurt. So it can be a very serious problem, to the point of causing your brain to swell, or your lungs to swell and bleed, and even death. So altitude sickness, the way it works is oxygen is delivered from our lungs to cells and tissues throughout the body by binding to hemoglobin in the blood. So it's this oxygenated hemoglobin that circulates to deliver oxygen where it's needed. So a really simple chemical reaction to show this would be that we have O2 that we breathe in, and it's exchanged in our lungs with our blood circulating through our lungs. It binds to hemoglobin to make oxygenated hemoglobin, HemO2. And this is an equilibrium process. It can go back and forth. So at high elevation, there's a lower pressure of oxygen. As we go up in elevation, the atmosphere pressure decreases. And so the pressure of O2 decreases, which means that the concentration of O2 decreases. So when the concentration of O2 goes down, what happens is that due to this being an equilibrium reaction and what's known as Le Chatelier's principle, the equilibrium reaction is going to readjust to make up for the change. So the change when you go to high elevation is that the concentration of O2 that you're breathing in goes down. So the reaction is going to start to favor the reverse reaction. It's basically going to try to make up for this loss of O2 by taking oxygenated hemoglobin and converting it back into deoxygenated hemoglobin and O2. And so when the reverse reaction is favored, you're going to have less oxygen bound to hemoglobin circulating in your body. You're going to have less of this, which is going to mean you have less oxygen available to your tissues and cells, which leads to altitude sickness. And I always talk about altitude sickness because I've gotten it. It's terrible if you've ever gotten it. It's just the thing to do if you do start to get it is go back down to lower elevation. And this is also why climbers sometimes carry oxygen with them, because if you start to get altitude sickness, if you introduce more O2, then it will shift the equilibrium back to making sure your body has enough oxygen circulating in the blood. Or if you just return to lower elevation where there's more oxygen in the air, higher pressure, higher atmospheric pressure, which means you're breathing in more O2 with each breath, that can also remedy the situation. Okay, our second example. 50% of the global food supply is dependent on inorganic nitrogen-based fertilizers. So nitrogen as ammonia, NH3, is synthetically produced for use in fertilizer through a chemical equilibrium reaction. So 50% of our food supply is dependent on using fertilizers that are produced with an equilibrium reaction. So the Haber-Bosch process for industrial production of ammonia, being able to produce ammonia at very large quantities, revolutionized the ag industry and helped increase food production worldwide in the early 1900s. So Fritz Haber was one of the developers of this process. He was awarded the Nobel Prize in Chemistry in 1918 for industrializing the production of ammonia. And so this is a equilibrium process. You take nitrogen gas and react it under high pressure with hydrogen gas to produce ammonia gas, and then this is further processed to produce ammonia for use in fertilizers. So as an equilibrium process, if you change, say, the concentrations of ammonia or hydrogen, it's going to affect whether this reaction favors the forward reaction to produce ammonia for fertilizer, or whether it favors the reverse reaction. So again, the definition of chemical equilibrium, it's the state in which the forward and the reverse chemical reactions occur simultaneously at the same rate, or they reach steady state. So a clue that a reaction has reached chemical equilibrium is when the concentrations of the reactants in the products no longer changes. If every time X plus Y, your reactants convert into products, you also get the products reverting back into reactants. Even though this process is happening all the time at the molecular level, overall, your concentration of products and your concentration of each of your reactants won't appear to change, because every time some reactant converts to product, some product is also going to convert back to reactant. If we look at a specific example of a chemical equilibrium reaction, if you take hydrogen gas plus iodine gas to make hydrogen iodide, 2HI, the reverse reaction, the forward reaction, H2 plus I2 to 2HI. If you map this out with reaction rate, the speed of the reaction along the y-axis, and the time or reaction progress along the x-axis, what you see is that at the beginning of the reaction, when you first start it, you initially have a lot of your reactants. It's like you just mix them together. And so they're going to instantly start reacting together. And so the rate of the forward reaction is going to be very high, which is why this blue line is way up high on the reaction rate coordinate. So the forward reaction is going to be very, very high, because initially all you have is the two reactants mixing together to make product. And initially, because you don't have any product formed yet, there's no reverse reaction because you don't have any product to turn back into reactants. So initially the forward reaction rate is high and the reverse reaction rate is low. But as the reaction proceeds, what happens is the forward reaction is producing some of your product to HI. And as HI is produced, it's able to revert back into reactants. And so as the reaction proceeds, the rate of the reverse reaction increases, because as you make product, that product's able to undergo the reverse reaction to turn back into reactant. And as reactants are used up, the rate of the forward reaction is going to decrease. If you think back to our lecture on what influences reaction rates, increasing the concentration of reactant is one way to increase the reaction rate. So if you decrease the concentration of the reactants because they're getting used up and converted into products, the reaction rate will slow down. And so as the reactants are converted into product, the rate of the forward reaction goes down. And as you make more product, the rate of the reverse reaction goes up, until eventually the rate of the forward and the reverse reaction, shown here, is equal. Make that a better looking circle. And the point at which the rates of the forward and the reverse reaction are equal, that's when we say equilibrium has been established. So you can pinpoint when equilibrium is established by looking at a rate diagram, reaction rate versus time. And when the rate of the forward reaction equals the rate of the reverse reaction, when they're both at the same point, that's when equilibrium has been established. That means that every time the reactants are converted into product, at the same rate, product is converted back into reactants. In terms of concentration, what that looks like is that initially, at the beginning of the reaction, you have a high concentration of your reactants because you're mixing together H2 and I2, so their concentrations are high. But as they're converted into products, the concentration of the reactants goes down. Meanwhile, you're producing product. And so initially your product concentration is low. You don't have any product made yet at the beginning of the reaction, but as the reaction proceeds, you're making more and more product, so its concentration goes up. Eventually, you have enough product that it starts reverting back into reactants. And when these rates are equal, the rate at which the reactants convert to products and the product converts back to reactants, the concentrations no longer change. So what that means is that every time reactants converted into product, at the same rate, product is converted back into reactants. And so the concentration curves will flatten out. And this point here, where the concentrations are no longer changing, they're a flat line, this is the point at which equilibrium is established. And so there's two ways to tell. You can look at the rate diagram. We go back a slide. You look at the rate diagram, and when the rates are equal, that's when equilibrium is established. Or you can look at a concentration diagram, and when the concentrations no longer change, That's also another way to tell that equilibrium has been established. I like this cartoon because it kind of shows what we just talked through with pictures and a diagram. So beaker 1 shows when the reaction is beginning, and you just have your reactants present, A plus B. And so when the reaction begins, there's no products formed yet. You have a high rate of collisions between your two reactants A and B, so the rate of your forward reaction is going to be high. As the reaction continues over time, you're still having product formed from the collisions between your reactants A and B, but slowly A and B are going to be used up as they're converted into your products, C and D. And so as A and B are used up, their concentration goes down, which means the rate of the forward reaction is going to decrease, and the reverse reaction is going to begin. C plus D are going to start reverting back into A plus B. This is going to continue until eventually you hit this point of balance between the forward and the reverse reactions, the point of equilibrium. Eventually, the rate of the forward reaction, A plus B, making C plus D, is going to be equal to the rate of the reverse reaction, C and D reverting back to A plus B. And this is when equilibrium is established. And the term dynamic is used here because when equilibrium is established, the concentrations of all of your reactants and products will be stable. It reaches steady state, but you still have the reaction happening. It's not like the whole reaction stops. You're still getting reactants converting to products and products converting back to reactants. It's just that overall on a macro scale, the concentrations of these individual reactants and products are no longer changing. But on the micro scale, on the molecular scale, you're still getting a reaction happening. It's just that every time the forward reaction happens, the reverse reaction also happens at the same rate. So let's do a quick check. So a state of blank is reached when the concentrations of all reactants and all products remain constant. And a blank is one in which the conversion of reactants to products and the conversion of products to reactants occurs simultaneously. So for this first blank, we're looking for the term that defines when the concentrations of reactants and products remains constant. So that's when equilibrium is reached, and it's chemical equilibrium because chemically, the concentration of your chemical reactants is equal, remains steady, as does the concentration of your chemical products. So chemical equilibrium is the first blank, which B is the only option for that. And then for our second blank, a blank is one in which the conversion of reactants to products and products to reactants occurs simultaneously. This is a reversible reaction. So that also makes sense there. So the answer is B. A state of chemical equilibrium is reached when the concentrations of all reactants and all products remains constant. And a reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactants occurs simultaneously. So in our next section, we're going to talk about equilibrium constants. So that was kind of the concept of equilibrium, what's happening at the molecular scale, that equilibrium reactions are reversible, and eventually in a reversible reaction, the rate of the forward reaction will equal the rate of the reverse reaction. When the rates are equal, the concentrations of products and reactants no longer change on the macro scale. We're going to talk about how to quantify this mathematically using what's called equilibrium constants in the next section. I'll see you then. Thanks for listening, and I'll see you next time.